In this video, we're going to take a look at something called comparison tests. This is another approach to determine whether or not a given series converges or diverges. So comparison tests are exactly what they sound like. We are going to compare a series where we don't know the convergence of that series, whether it converges or diverges, and we're going to compare that series to one that we do know the convergence or divergence of, and use that comparison to determine basically the result. So we'll compare the convergence of an unknown series. Let me phrase it differently. We'll compare the unknown convergence. Let's say that. So I don't know whether the series converges or diverges. So the unknown convergence of a series to another one that we do have, so to a series with known convergence. Okay, so for example, let's say that we're looking at the series, I'm taking the sum from n equals 1 to infinity of 1 over 2 to the nth plus 1. I don't know whether this series converges or diverges because it's not a series that we've dealt with before, but we do know that 1 over 2 to the nth plus 1 is always going to be less than 1 over 2 to the nth. And 1 over 2 to the n is a geometric series, which we've looked at in previous sections. So because our terms in our series are less than these terms in the geometric series, if I can show that the geometric series converges, then that will also mean that this series must also converge because it's always less than this one. So let's take a look at the geometric series. If I look at the sum from n equals 1 to infinity of 1 over 2 to the nth, that's equal to, if we break this up, so remember the geometric series, the form of a geometric series is the following. We want the sum from n equals 1 to infinity of a times r to the n minus 1 power. This is the form of the geometric series that we're using. So in our case, if I want to write this in that same form, right now I can think of this as being the sum from n equals 1 to infinity of the number 1/2 raised to the nth power. I want to rewrite it so that the power is n minus 1. And to do that, all I need to do is factor out an extra version or an extra factor of 1/2. So if I factor one of the 1/2s out, that'll leave me with a 1/2 to the n minus 1 power sitting next to it, right? So 1/2 to the first power, 1/2 to the n minus 1th power. When you multiply them together, you get 1/2 to the nth power. The powers would sum together. So this plays the role of my a, this is my r, and obviously n minus 1 is pretty explicitly written right up there. So we said that this converges basically whenever the value of r is less than 1, or the absolute value of r is less than 1. And so in this case, not only does it converge, but in fact we know that this thing converges to a specific value. So this will converge to the formula that we had was a over, let me not write this here, this thing up here converges to a over 1 minus r. That was the formula. And so for us, this thing converges to 1/2, there's my a on top, over 1 minus r. r is also 1/2. So I get a half over a half, which is equal to 1. So this sum right here, this series converges to 1. This series, I don't know what it converges to, but I know that these terms are all less than these terms, and so it must also converge, right? I'm adding an infinite number of terms here, it converges to 1. The terms here are bigger than the terms here, so if I'm adding these ones, they must also converge. It's no way for this to diverge off to infinity if I'm adding a bunch of smaller pieces than the pieces down here, which converge. So this is the idea. So by our comparison tests, and in fact, this is what we're going to call a direct comparison test, which I won't even introduce that yet. We'll talk about that in just a minute. So let me just say this. So the sum from n equals 1 to infinity of 1 over 2 to the nth plus 1 must also converge. So now let me formally state the direct comparison test, and we can do another example. So basically what we're looking for, and just keep this in mind, I decided to compare this to 1 over 2 to the n, which I do know the behavior of. And this one, 1 over 2 to the n plus 1, is less than 1 over 2 to the n. In that case, if this one converges, then this one will also converge. But if this inequality were flipped, if instead I had 1 over 2 to the nth minus 1, so that this side was greater than this side, that wouldn't be a good comparison to make, because I would, even though this one's converging, these terms would all be bigger than these terms, and I wouldn't necessarily be able to draw that same conclusion. So you've, again, got to be conscientious about how you set up your comparison. So we'll talk about that here. So in our direct comparison test, which is exactly what we just did above, we're going to suppose that we have two different series. And in this case, we're going to assume that they both have just only positive terms, no negative terms, no flip-flopping back and forth, just make our life easy. So let's suppose that we've got the sum of a sub n's and the sum of a bunch of b sub n's. And just for the sake of expediency here, I'm not going to write the n equals 1 to infinity, n equals 1 to infinity on all of these. Just whenever you see this sum, assume that we're talking about an infinite sum. So suppose that these two things are series with all positive terms. So again, we're just doing that to make our life a little bit easier. Then there are two things that can follow from this. So item 1. If we have that the sum of the b sub n's converges, so let's say basically we don't know the behavior of the a sub n series, but we do know the behavior of the b sub n series, and that b sub n series converges, and a sub n is less than or equal to b sub n for all n, then, let's see if I can fit it all in one line, the sum of all the a sub n's must also converge. Let's zoom out just enough that I can fit this all on one page. Let's write that a little nicer. Converges. Oops. And the second one says that if b sub n diverges, and all the terms of a sub n are always larger than those terms on the b sub n for all n, then the sum of a sub n will diverge as well. So this is what I mean by being careful about how your comparison is set up. If you're trying to prove divergence, you need your a sub n's to be bigger than your b sub n's. You need your unknown terms to be bigger than the terms in the series that you do know. If you're trying to prove convergence, then you need the terms in your unknown series to be smaller than the terms in your known series. So keep that in mind. So let's do another example of this. And let's say I'm looking at the sum from n equals 1 to infinity of 1 over n squared plus 3. So in this case, I'm going to suspect that this is going to converge because it looks similar to a p-series that converges. So what should I be comparing this to? In this case, the direct comparison that I want to look at is the p-series with p equal to 2. So I want to take note that 1 over n squared plus 3 is always going to be less than or equal to 1 over n squared. Right? This has a larger denominator than this one, and when you make the denominator larger, the overall term gets smaller. So this will be smaller than this for all values of n. And so this is the one I want to do the comparison with, which is going to be a p-series. So we know that the sum from n equals 1 to infinity of 1 over n squared converges by our p-series test with p equal to 2, which is greater than 1. Right? The cutoff was always whenever p is greater than 1, a p-series will converge. So if the sum from n equals 1 to infinity of 1 over n squared converges, and 1 over n squared plus 3 is always less than or equal to 1 over n, then by the direct comparison test, the sum from n equals 1 to infinity of 1 over n squared plus 3 will also converge. And it converges again by the direct comparison test. So this is going to be an important thing to get in the habit of, is not just specifying whether something converges or diverges, especially on the exam, but saying how you know. A lot of them you're just going to kind of know, or you're going to be able to do like the stuff that we just did here. You hopefully will get to a point where you can recognize convergence of a p-series really quickly. You can more or less make this comparison in your head and know right off the bat, yes, this is going to converge. And you can just say, yes, it converges. But that's not sufficient work to show on an exam. I want to see the thought process. And so get used to writing stuff out like this, specifying that we know that this term or this series converges because it's a p-series with p equal to 2, which is greater than 1. Specify that we're using the direct comparison test and that relies on this particular inequality. And I should write, I missed my squared there. Now that is correct. So just make sure that you actually spell things out. This is going to be a section where it's important to get in the habit of actually explaining, even if you can do stuff in your head, explaining what you're doing and just getting good at understanding and reasoning through these problems. So the direct comparison test works great most of the time for when we have a comparison like this, where we've got some unknown one that's similar to one that we do know. But what happens in the case where instead of this being a +3, what if it had been a -3 instead? What would we do in that case? Because now this wouldn't hold anymore. I would suspect that the behavior is probably still pretty similar to a p-series, right? Doing a -3 here isn't going to change that much, but how can we be sure? And so this brings us to a second test, a different type of comparison test that instead of being a direct comparison test, where we directly compare the terms in the series, we're going to look at something called a limit comparison test, where we're going to compare the limits of those terms in the series. So the limit comparison test. So the limit comparison test says the following. Again, suppose that we have two series, the sum of all the a sub n's and the sum of all the b sub n's, that are both series with positive terms. If we look at the following, the limit as n goes to infinity of a sub n over b sub n, a sub n over b sub n, and we get a constant. This constant is a finite number, and we'll say strictly positive because all the terms themselves are supposed to be positive. So the ratio, if all these terms are positive, should also be positive. So equals a constant, which is, so C is finite, and C is greater than 0. Then both series exhibit the same behavior. So if the known one diverges, then so does the unknown one. If the known one converges, so does the unknown one. So both series either diverge or converge together. So they have the same behavior. This is going to be something that we can use on those situations that I just talked about a minute ago. Let's say, for example, we do the exact same problem that we just had, where I've got the sum from n equals 1 to infinity of 1 over n squared, what did I say, minus 3. In this case, 1 over n squared minus 3 is a larger number than 1 over n squared. Right? Again, and we're assuming in this case that so the denominator is smaller, the numerator, or sorry, if the denominator is smaller, the overall term will be bigger. And again, we have to assume that these terms are positive, right? You can't plug in n equals 1 here. N equals 1 is misleading, because if I plugged in n equals 1, we would get 1 over 1 squared, which is 1 minus 3. So I'd get negative 2 on the bottom. I'd get negative 1/2 here, whereas over here I'd have 1. This inequality wouldn't be true. But it's not true because the terms are not positive. We need both series to have positive terms. Our a sub n, our unknown one, and our b sub n, our known one, both have to have positive terms. So this was an unfair number to start off with. This was a bad example. Let me change it to n equals a value that'll give us positive, so that would start at least at n equals 2. So I'll start it there. Okay, so now these terms are all strictly positive, and this comparison will work. So I can't do a direct comparison. This converges, but this we don't know because it's not smaller than this. So I can't claim convergence on this term by the direct comparison test, because the direct comparison test would require this term to be less than or equal to this term over here. So direct comparison won't work. But just because direct comparison doesn't work doesn't mean that the behavior should really be that fundamentally different. They still look like they're going to have very similar behaviors. And so we can verify that using a limit comparison test. So let's compare the limit of this a sub n. So if we call this our a sub n, and let our b sub n be the one that we know converges, right? This converges by p series. And again, I shouldn't say that that term converges, but we're going to let b sub n be equal to that. the sum, the series from n equals, doesn't matter, so we start at 1 or 2, but this converges. The series is what converges by p series. By p series with p equal to 2, which again is greater than 1, so it converges. So let's compare the limit as n goes to infinity of a sub n over b sub n. So for us, a sub n is 1 over n squared minus 3. B sub n is 1 over n squared. And I'm writing this, but I forgot my limit, so let me write it with the limit. So the limit as n goes to infinity. It's a hard habit to get into. Please don't forget to write your limits. But here's the ratio. Here's my a sub n on top, my b sub n on the bottom. Instead of having a fraction divided by another fraction, we can clean this thing up and write this as the limit as n goes to infinity of n squared over n squared minus 3. And what is that limit? For large values of n, this minus 3 is totally inconsequential. And I can see that looking at the power on top and the power on bottom, they're the same. I have an n squared on top and an n squared on bottom. So all we need to do is look at the highest powers of n and compare them. In this case, the two highest powers of n are both n squared, and this limit is going to be equal to 1. So it's a constant that's positive and finite. So positive and finite. So we get the requirement here satisfied, that we need to get a constant that's finite and positive. So both series are going to have the same behavior. Since we know that this series converges, then by the limit comparison test, the sum from n equals 2 to infinity of 1 over n squared minus 3 will also converge. So that's the idea. In general, our goal is to just come up with the hardest part is coming up with the correct series to compare to. So let's do a couple more examples and just see how this goes. Let's try, and this goes for both direct comparison and limit comparison. Let's do the sum from, again, n equals 2 to infinity of n over n cubed minus 1. And let's see what we should compare that one to. So if this is my a sub n, what should our b sub n be? So let's try a b sub n that we know the behavior of. Looking at this, again, as n starts to get large, so as we continue to add terms way down the line, this whole thing is going to start to look like essentially just n over n cubed, because the minus 1 is going to become inconsequential for large values of n. N over n cubed is essentially comparing the highest power on top, a first power, to the highest power on the bottom, which is a cubed. This is going to behave largely like 1 over n squared again. So this is what I want to use in my comparison. We want to look at the sum from n equals 2 to infinity of 1 over n squared, which we just determined in the previous problem. This converges, again, by the p series with p equals 2, which is greater than 1. So I already know the behavior of this one. If I compare a sub n and b sub n, and the ratio of those two things, and I look at the limit as that ratio goes to infinity, as the ratio as n goes to infinity, and I get a constant, then it tells me that they have the same behavior. And I think that's what we're going to find momentarily. So compare the two values. I want the limit as n goes to infinity of a sub n over b sub n. And in this case, my a sub n is n over n cubed minus 1, and my b sub n is 1 over n squared. And again, terrible habit, don't forget your limit. Limit as n goes to infinity. I haven't evaluated that limit yet. So n over n cubed minus 1 over 1 over n squared. And if we turn this fraction divided by a fraction into a fraction times the reciprocal of the other fraction, we will get our limit as n goes to infinity of n over n cubed minus 1 times n squared over 1, which is the limit as n goes to infinity of n cubed over n cubed minus 1. And by the same argument, this limit is going to be 1. I just need to look at the highest powers of n, they're both cubed, and I just compare the ratio of their coefficients, 1 over 1, to give me a ratio of 1. So, by the limit comparison test, our series from n equals 2 to infinity of n over n cubed minus 1 converges. It doesn't necessarily converge to 1. This 1 has nothing to do with what this thing converges to. It's just that it has to be any finite constant. So it is going to also converge. We can't specify what it's going to converge to. Let's try another one. Let's look at the sum from n equals 1 to infinity of 2 over the square root of n plus 2. So again, I'm going to let this be my a sub n, and we need to figure out what our b sub n should be. So in this case, I'm going to try something that has a similar form to this, right? The square root of n is going to be important, the square root of n in the denominator, but one that's easy to deal with, one that I can figure out the behavior of. So I'm just going to try having my b sub n be equal to 1 over the square root of n, because it looks like they're going to have largely the same behavior. This one has a 2 on top instead of a 1. I could put a 2 here instead if I wanted, but it won't make any difference. This term, if we look at its corresponding series, we know that the sum from n equals 1 to infinity of 1 over the square root of n, this thing diverges. And it diverges again by the p-series test. With p equal to the 1/2, right? N is being raised to the 1/2 power in the denominator, which is less than 1. So it diverges. So if I wind up getting the ratio of a sub n over b sub n, and taking that limit as n goes to infinity, and I wind up getting a constant, then I know that this will have the exact same behavior as this. And so that's what we will see. Let's give it a shot. Let's take the limit as n goes to infinity of a sub n over b sub n. So for us, that's going to be the limit as n goes to infinity of 2 over the square root of n plus 2 over 1 over the square root of n. And again, we'll simplify this, multiply by the reciprocal instead of dividing, and we'll get 2 over root n plus 2 times root n over 1. And this limit cleans up to 2 root n on top over root n plus 2 on the bottom. And that limit is going to be 2. right? Again, what's the highest power of n? It's half power on the bottom, it's a half power on the top. Lower powers of n to the 0th, this constant term, become irrelevant for large values of n, and so I just need to look at the ratio of the coefficients. 2 on top, 1 on the bottom, the ratio is going to 2, which again is a finite constant that is positive. And so it's greater than 0, and again, I should have written that here, also greater than 0. It needs to be greater than 0. If it's not greater than 0, we don't know what's happening. It won't necessarily give us the information we need. But this is greater than 0, and we wind up getting enough to show that, therefore, by the limit comparison test, the sum from n equals 1 to infinity of our square root of, 2 over the square root of n plus 2, it must also diverge. It diverges in the same way that this series diverges. So hopefully you're kind of starting to get the hang of these, see the pattern. We could try another one if we wanted to. But ultimately it's going to become something where you should know the answer before you start doing the problem. You should have a sense, or at least a good guess, for what you expect the behavior to be before you even do the problem. So let's do another example and see if we can anticipate what the behavior is going to be before we formally justify it. So let's see, I'm going to say I want the sum from n equals 1 to infinity of n squared plus n plus 1 in the numerator. And let's do, I don't know, n to the 4th plus n squared in the denominator. So again, this is my a sub n. Is this thing going to converge or diverge? I know from looking at it that it is going to converge. I know it's going to converge because for large values of n, as we get up towards the infinity here, the only powers that become important are this n squared on top and the n to the 4th on the bottom. And if I look at just the ratio of those highest powered terms, this thing's really going to be behaving like a 1 over n squared. You can kind of cancel the n squared up here with 2 of the n's that show up down here and get this is going to behave overall like a 1 over n squared for large values of n. And I know that 1 over n squared converges by the p-series test. So I know ahead of time this is going to converge, but now I just need to formally show that. So I will anticipate that my b sub n needs to be 1 over n squared. That's the term that I'm going to compare this to. We know that the sum from n equals 1 to infinity of 1 over n squared converges. And again, by the p-series with p equal to 2, which is greater than 1. So all I need to do now is verify that the limit as n goes to infinity of a sub n over b sub n, which is the limit as n goes to infinity of the big ugly term here, n squared plus n plus 1 over n to the 4th plus n squared over 1 over n squared, which simplifies to the limit as n goes to infinity of n squared plus n plus 1 over n to the 4th plus n squared times n squared over 1, which is going to be the limit as n goes to infinity of distributing that n squared through. We'll get n to the 4th plus n cubed plus n squared over n to the 4th plus n squared. The lower powers of n don't matter. For very large values of n, all that I care about is the highest powers of n and what is their ratio. And the ratio of the n to the 4th on top and the n to the 4th on the bottom is 1, which is greater than 0. So we get a constant that is positive. So by the limit comparison test, have the same behavior, which means that the sum from n equals 1 to infinity of n squared plus n plus 1 over n to the fourth plus n squared is going to be that this thing converges. Its behavior is that it converges. Okay, so hopefully you start to get the hang of those as you kind of see them. This last part isn't something that's from the book, but I think it's probably the most important takeaway from this. The idea of comparing an unknown function or an unknown series to one that we do have known behavior for is really important. So when possible, the direct comparison test is super simple. When the direct comparison doesn't necessarily work, often the limit comparison test will work. And in fact, the limit comparison test will work, as near as I can tell, it should work for any one of the direct comparison test problems as well. So if you have a problem that you can do a direct comparison on, that's fine, but you could probably also get away with doing the limit comparison test. So here's a big important note on direct comparisons, and just on comparisons in general. It's going to be really important to be able to look at a function, or in this case, look at an a sub n term in a series, and be able to figure out that for large n at least, what its behavior is. So it's important to be able to look at this one here and suss out the fact that for large n, this plus 1, this n squared, these are irrelevant for large n's. All that matters is the biggest term on the top compared to the biggest term on the bottom. The biggest term on top is an n squared, the biggest term on the bottom is n to the fourth. Overall, this thing's going to behave like a 1 over n squared for large values of n. That is a really important thing to be able to sense. And so I want you to have a sense of the behavior of these different functions. What is the behavior of different functions? Or different, not even functions. Function's not the right word. Different a sub n's as n goes to infinity. So basically, oftentimes they will be written in terms of some sort of function. Let's think of them as functions in terms of n, and we want the limit as n goes to infinity. So as n goes to infinity, here's a really important idea. The natural log of n is going to be a function that's much, much smaller. So when you see these double inequalities like this, it means not just less than, it means much, much less than. It means basically orders of magnitude less than. But the log of n is much, much less than n, which is going to be much, much less than n squared, which is much, much less than, in fact, let me sneak in a few others. It's much, much less than the square root of n, which is much, much less than n, which is much, much less than n squared, which is much, much less than n cubed, and so on, through all the possible values of the powers up here, including fractional powers. All of those polynomial terms, basically, right, that are just different powers of n, they're all much smaller than any, and a is fine, a to the n. So this includes e to the n, like exponentials with the natural exponent, but same as 2 to the n, or 3 to the n, or 4 to the n. They're all much smaller than these exponentials, assuming a is greater than, not 0, a is greater than 1, under that assumption, which itself is much, much less than n factorial, if you're familiar with the factorial function, which is much, much smaller than n to the nth. So this gives us a hierarchy. Hierarchy of what we can think of as function growth, in a sense. As n goes to infinity, all of these terms are going to infinity, but it's telling us how quickly they grow. All terms go to infinity, but they approach it at vastly different rates. Oops, vastly different rates. And so again, this hierarchy that I've written here isn't in the book, but it's a really important thing to have in the back of your mind. And so I would honestly recommend getting this down. Make sure that you have this more or less memorized. And just as a note, again, when you see that symbol, it means much, much less than. So basically, we're talking about orders of magnitude. And what it's telling us is, again, for large n, as n goes to infinity, it doesn't matter. You could have n to the 1,000,000th power. So a polynomial with the power of 1,000,000. N to the 1,000,000 is going to grow more slowly than even the number, a tiny number, 1.1 to the nth power as n approaches infinity. If n gets large enough, eventually even 1.1 to the n, this exponential growth, with a base term that's just slightly bigger than 1, is going to grow infinitely faster than even n to the 1,000,000th power, or n to the 1,000,000,000th power, n to the 1,000,000,000,000th power. Put any finite power you want up there, and this exponential is going to grow faster. So basically we have, down here we have logs. All of these terms you can think of as sort of, powers of n, power functions, polynomials. We have exponentials right here. We have factorial. And this doesn't really have a good name, just, it's what it is, n to the n. And, what would grow faster than n to the n? N to the n to the n, right? You can play this kind of stupid game as much as you want, but this is probably about as extreme as you're going to see in practice. This is an absurd one. So just keep that in mind. As n goes to infinity, a function that's in one of these kind of categories, the way I've categorized them here, can never eclipse something in the next category up. So any exponential as n goes to infinity is going to be larger than any power function that you can pick. And this is a really kind of, in many ways, kind of surprising, crazy idea. So for example, if I wanted to compare two functions, let's say I wanted, again, so as n goes to infinity, this is the scenario we're talking about. As n goes to infinity, how does n log n compare to n squared? Well, basically I'm saying that this one times anything to the left of it, anything smaller than it, when I multiply those together, there's no combination of this times stuff to the left of it that's going to make it eclipse something that's further to the right. So it turns out n log n is much, much smaller than n squared. That doesn't necessarily work within one of these categories. So power functions, right? I can come up with a combination of stuff to the left of n squared here. I would just need to take n and another n and another n, and that would be bigger. But when you start jumping categories, so from power functions to logs, there's no combination of a lower power function plus anything in an entirely lower category that's going to jump you up to eclipse a higher power function. I hope that's clear what I mean by that here. What about n factorial times a to the n? So an exponential times a factorial function. I multiplied these together. How do they compare to n to the nth? Doesn't matter. These are both in smaller categories than this. Even their combination is not enough to eclipse n to the nth. N cubed times a to the n. How does that compare to n factorial? Same idea. N factorial is in a larger category. There's no combination of this and anything to the left that can make these things supersede this. So it's going to be much, much less than that value there. So what I've done is looked at these individual functions. They all go to infinity as n grows to infinity. But for us, what we tend to care about are terms that look like the reciprocals of these, right? Most of the terms that we've got here look like 1 over an n squared, or 1 over a square root of n. I did that somewhere here. 1 over a square root of n. So let's think about what happens when we look at the reciprocals of these. What this means is the following. If I look at 1 over the log of n, just to make it clear, let me put parentheses around it wherever I write it so it's easier to read. So 1 over the log of n, and 1 over the square root of n, and 1 over n, and 1 over n squared, and 1 over n cubed, and then 1 over a to the n, and 1 over, let's do n factorial, and 1 over n to the nth. When we take the reciprocals, all of these are now going to 0 as n goes to infinity. But these ones, because the denominator is going to 0 much slower, these terms are going to be much larger than the terms as you move right. So now our inequalities switch directions. Those are ugly. There we go. So think about which of these terms are going to converge and which will diverge. In a series, if these, so let me say this, let me write out some words here. All of these terms, all of these go to 0 as n goes to infinity. But some go to 0 more quickly than others. This one goes to 0 slowly because the denominator goes to infinity slowly. This one goes to 0 very, very, very quickly because the denominator goes to infinity very, very, very quickly. So all these terms are going to 0. If these terms appear as the terms in a series, so if they appear as the a sub n in a series that looks like the sum from n equals 1 to infinity of a sub n, not all of them will converge. So we said this before. The terms need to go to 0. In an infinite series like this, if it's going to converge, eventually the a sub n's need to go to 0. We eventually need to be adding on 0 additional terms. But that's not sufficient to show convergence. They have to go to 0 sufficiently quickly. Where does that cutoff occur? That cutoff occurs right here at 1 over n. So basically, if we write these out again, if I have terms, so let's write this again. If our a sub n is one of these, 1 over the log of n, or 1 over the square root of n, or 1 over n, all of these are going to diverge. But the second n is the power of n is greater than 1 in the denominator, so n to the 1.1, n squared, n cubed, fractional powers in between, yada, yada, yada. 1 over exponentials, 1 over factorials, 1 over n to the nth. Here's our cutoff right here, basically. And it's really at this one. So I'm going to do it through the 1 over n. All of these diverge, whereas all of these converge. So over here, basically we've got situations that, for example, like right here, this one is a geometric series. Right? This is a geometric series. These are the various, really all of these in here are the p-series. These are ones that we've talked about. And the p-series, the cutoff was n to the p, where p equals 1. If p is greater than 1, it converges. If p is equal to 1, it diverges. So it could literally be 1.00000001. I could have 1 over n to the 1.00001. That's going to converge. But the second I change it to 1 over n to just the first power, that diverges. That is all the difference it takes. So let me erase those. But this is a really important cutoff to keep in mind. Terms that look like this are going to diverge. Terms that look like this are going to converge. If you can figure out which one of these types of things is going to, when you're doing your comparison test, if you can figure out which one of those types of functions is going to be the type of function you should be comparing to, like we did here and here, you can immediately have a sense of whether or not your answer is going to converge or diverge if you can correctly pick out what one of these functions to compare it to. So keep that in mind. So again, this isn't in the book, a comparison table like this, but I'd very strongly recommend that you memorize this. This is probably, for all the computations we're going to be doing, this is the most important thing. I want you to be able to have an intuition for what the behavior of your series is going to be before you even start trying to apply a test. The tests aren't meant to just be guesswork. The tests are meant to be a rigorous way to verify convergence or divergence, but you should already have intuition before you even start that process. And this should give you the intuition that you need. These functions over here will all diverge. If these show up as your a sub n in your series, you're getting divergence. If you get something that looks like any one of these over here, oops, and this last one I wrote incorrectly, so don't copy this down. That should be n to the nth power. If it's one of these over here, your series is going to converge. And the cutoff occurs right here at 1 over n. Any combination, if you multiply any of these together, right? So 1 over n log n, that's still going to diverge. 1 over the square root of n log n, that's still going to diverge. As long as you're combining one of the p-series with log of n, and the p-series is one that diverges, adding that log n is not going to help you. Same thing over here on this side. Any product of these terms over here will make the whole thing converge. Any one of these things over here mixed with something on this side will also converge, because, you know, even if I've got a 1 over n squared and I multiply that by another 1 over square root of n, well, I've now got 1 over n to the 5 halves. I've made it even bigger. So if these things are, again, these terms, I've made the power bigger, I should say. These terms go to 0, these terms go to 0, but the cutoff for which diverge and converge occurs right here at 1 over n. So just keep that in mind.